Quantum computing. Just the phrase sounds like science fiction, doesn't it? Qubits, entanglement, superposition. It's the kind of language you'd expect in a Marvel movie or an MIT lab, not something shaping your future. But here's the twist. Quantum computers are no longer just a theoretical dream. In 2025, they are real, functional, and already rewriting the rules of what's possible in technology. If you're even a little curious about how the next computing revolution could change everything from medicine to national security, then buckle in. And while you're here, don't forget to like this video and subscribe. We bring you cutting-edge tech stories that go beyond the headlines. Stories that just might give you a glimpse into the world you'll be living in 5 years from now. So what exactly is a quantum computer? Let's put it this way. A classical computer, the kind you're watching this video on, processes information using bits. These bits are either 0 or 1, on or off like tiny switches. But quantum computers use qubits, which can exist in a state of 0, 1, or both at the same time. This strange ability, known as superposition, is just one part of what makes quantum computers exponentially more powerful at certain tasks. But that's not all. Qubits can also be entangled, meaning the state of one is instantly linked to another, even across vast distances. This allows quantum machines to process vast amounts of information simultaneously, something classical computers can't even come close to. Now, before we get too far into the hype, let's address a common misunderstanding. Quantum computers are not simply faster computers. They don't run YouTube, games, or edit videos better. They're not going to replace your laptop or your iPhone. Instead, quantum computers are designed to solve a very specific class of problems. Ones so complex that even the most powerful supercomputers in the world would need millions of years to solve them. Problems like simulating molecules for drug discovery, optimizing global logistics routes in real time, or breaking certain types of encryption that keep our digital world secure. Let's talk about where we are now, in 2025. Google made headlines back in 2019 when it claimed quantum supremacy, the first time a quantum computer solved a problem a classical one could not. That experiment, while impressive, had little practical use, but it was proof of concept. Since then, companies like IBM, Rigetti, IonQ, and startups like PsiQuantum have been racing to build scalable quantum machines with real-world capabilities. IBM, in particular, has been making steady progress. Their roadmap includes releasing a 1,121 qubit system by the end of this year, called Condor. And that's not just a bigger machine, it's a smarter one. Their new architecture allows multiple qubits to work together more reliably, reducing the error rates that have long plagued quantum systems. Error correction is actually one of the biggest barriers in quantum computing. Unlike regular bits, qubits are incredibly fragile. A tiny vibration, a change in temperature, even a stray magnetic field can cause them to lose their quantum state. This is called decoherence, and it happens in microseconds. To fight this, scientists have to cool quantum chips to near absolute zero, colder than outer space, and surround them with elaborate shielding. And even then, they make mistakes. That's why so much of the work in this field isn't just about adding more qubits, but making them more stable and useful. So how are quantum computers being used today? Believe it or not, some are already online. IBM and D-Wave, for example, offer cloud-based quantum access for researchers and companies. In 2024, a research team used a quantum computer to simulate the behavior of a complex molecule involved in nitrogen fixation, something classical computers couldn't do efficiently. In finance, some hedge funds are experimenting with quantum algorithms to optimize portfolios. In logistics, Volkswagen and DHL have explored using quantum models to improve delivery routes and traffic flow. And in cybersecurity, quantum cryptography is being developed to create encryption methods that even quantum computers can't break. But for every success story, there are 10 headlines that stretch the truth. So let's talk about the hype. One of the biggest myths is that quantum computers will break the internet by instantly cracking encryption. While it's true that quantum machines could break RSA encryption, a method that secures most of our internet traffic, it's not happening overnight. Experts believe it could take 10 to 20 years before quantum systems are powerful enough to break such encryption reliably. And the good news? Governments and tech companies are already working on quantum-resistant algorithms. The National Institute of Standards and Technology, NIST in the US, is close to finalizing a new set of cryptographic standards that can withstand quantum attacks. Another overblown claim is that quantum computers will solve cancer or invent new physics. While the potential in healthcare and material science is real, it's important to understand that quantum computers are tools, not miracle workers. They don't generate answers on their own. They need algorithms, models, and massive collaboration to make meaningful progress. That said, drug companies are watching closely. Quantum simulations could one day allow scientists to design new medicines atom by atom, dramatically speeding up the discovery process and reducing reliance on costly, time-consuming lab experiments. Let's also talk about national security. China, the US, and Europe are in a silent quantum arms race. In 2023, China unveiled a prototype quantum satellite that could transmit encrypted messages using quantum key distribution, a method that's nearly impossible to intercept or decode. The US is responding with the Quantum Computing Cybersecurity Preparedness Act, encouraging federal agencies to upgrade their encryption protocols ahead of time. This quiet battle for quantum advantage could shape the future balance of global power, not through weapons, but through who controls the most advanced algorithms and computing power. Meanwhile, companies like Microsoft are pursuing a completely different approach called topological quantum computing, which they believe will be more stable and scalable in the long run. Rather than using trapped ions or superconducting qubits like most competitors, Microsoft is betting on exotic particles called Majorana fermions. If they're right, their system could leapfrog the entire field, but that's still a big if. And then there's the startup scene. Venture capital is pouring into quantum technology at an accelerating rate. In 2025 alone, over $3.5 billion in private funding has been invested in quantum startups. PsiQuantum, based in Palo Alto, claims it can deliver a 1 million qubit quantum computer by the end of the decade using silicon photonics instead of superconductors. That would be a game changer. But again, it's not guaranteed. Building a quantum computer is like building a rocket in the dark. Every new component introduces challenges you didn't see coming. So where does that leave us? In the midst of a transformation, but not a revolution, at least not yet. Quantum computing in 2025 is very real, very promising, but also very misunderstood. The tech is not ready to replace classical computing, nor is it useful for every task. But in certain domains, molecular chemistry, optimization, cryptography, it's already proving its worth. Think of quantum computers as the early airplanes of the Wright brothers era. They're clunky, expensive, and limited, but undeniably real. And just like early aviation changed how the world moved, quantum technology could change how the world thinks, calculates, and secures itself. As for the future, quantum computing may become something most people never directly use, but that still touches every part of life. Your medication, your supply chain, your digital privacy, your country's infrastructure. They may all be optimized or protected by quantum systems operating quietly in the background. The real challenge isn't just building the hardware. It's training the next generation of engineers, physicists, and developers to use it wisely. So the next time you hear someone say quantum computing is all hype, remind them that the internet once sounded like a pipe dream too. And look where we are now. If history is any guide, the biggest changes usually start small, slow, and full of doubt until they're everywhere. Thanks for staying with us on this deep dive into the quantum world. If you enjoyed this video and want more breakdowns of the future of tech, we've got much more coming your way. From brain-computer interfaces to AI cities. See you in the next video.